The topic for today is to replace multiple cells in parallel. Replace multiple cells which are in parallel by a single cell. This is the purpose of today's topic. Now, the cells are not as we used to see in smaller classes. Now, the cells have an internal resistance also. Any cell is represented like this. This is the internal resistance of a cell that a cell has because of the flow of ions inside it. Either it is solid or liquid, in linear cell, voltaic cell, any cell, every cell has an internal resistance. By E, we mean its EMF. Okay, that is the maximum possible value that it can provide when it is not in use. Now, we have to use two formulas. The first formula is the relation between EMF and potential difference. So, we have to know for solving this topic. We have to know the difference. Okay, so what is the difference between EMF and potential difference? I have already discussed it, so I will discuss it in just a single line. EMF is the maximum potential difference. EMF is the maximum potential difference when current is zero. That is when cell is open. And potential difference is what? Potential difference is equal to the voltage received by external resistance. Voltage received by what? By external resistance. Okay, you can say EMF is like your salary. Suppose your salary is 10,000 rupees. So your EMF is 10,000 rupees. But when you reach home, you can only provide 9,500 rupees to your house. 500 rupees are spent to reach home. Suppose 500 rupees is the fare. So 10,000 is the EMF and 9,500 is the potential difference. So suppose let's start with two cells. Okay. First of all, let me introduce you to one more formula. If it is a cell, its internal resistance is E, is R, its EMF is E. If it is connected to an external resistance R, let me call this point A and B. So this external resistance R, it is also connected to the point A and B. You can remember it like this, that when connecting wires are used, every point has the same potential, so every point is same. Okay, so we can define potential difference by two methods. Either we can define potential difference as whatever this capital R receives is potential difference, or potential difference can also be said to be whatever be the value that is present between A and B. Now, how to get the relation between EMF and potential difference? To know the formula, I can directly write the formula. The formula is EMF equals to voltage plus I into my R. E is the EMF, obviously. V is the voltage or potential difference. I is the current and R is the internal resistance of cell. Okay, we have already discussed it, but we have to use this formula. Okay, this value I into R, it is the voltage that the cell uses by itself. So it is like expenditure of the cell. Okay, the worse the cell is, the more will be the value of I into R. So this is the general topic about potential and EMF. So we will use this formula, that potential difference between any two points. If A is positive and B is negative, then VAB means VA minus VB, because the point which is connected to the positive terminal has higher voltage as compared to the point which is connected to the lower potential. I am sorry if this is B, this point will not be B, it will be C. But I am considering this whole setup as a single cell, so I am using VAB. This is the cell that is in packing. So potential difference across 2 points is given by the formula EMF minus I into R. And here you have to remember that R is the internal resistance of the cell and not the external resistance. Okay, so let me revise. What was our aim? Okay, what is our aim? Our aim is to replace multiple cells which are connected in parallel by a single cell. So let's start by two cells. Okay, suppose we have two cells which are connected in parallel to an external resistor. These are the two cells which are connected to an external resistor, let's say capital R. The value of EMF of this cell is E1, the value of EMF of this cell is E2, the internal resistance are small r1, small r2. Now I can call this point as A, this point as B. So I can say that the external resistance is connected between the points A and B. So I want to replace these two cells by a single cell. By a single cell, I mean that if I connect a single cell to the same external resistance, then I will call its EMF as the equivalent of these two cells only and only if this cell alone does the work which these two cells are doing in combination. And what these two cells are doing in combination, let's say these two cells in combination are flowing a current I through this external resistance R. So if this single cell whose EMF is E dash, whose internal resistance is R dash, if this cell also flows the same current I through this external resistance, then I will call E dash as equivalent of these two cells. So our aim is to find this. And what is R dash? R dash is similarly equivalent resistance of these two cells. Okay, so this is the aim of our today's topic. So how I will solve it? Okay, let's focus on the point. Let's say why I have taken the direction of current from here to here, because this is the positive terminal of the battery, this is a negative, this is also positive, this is a negative. We know that for a cell the current flows from positive towards negative. So I am taking the liberty of assuming that the current is flowing here to here. If I draw a single cell like this, then also we show current like this. The current is going out from this side and it is coming from this side, because this side is positive and positive side generates current and the negative side terminates current. So I'll take the liberty. Okay, now I'm saying that these two cells in combination are flowing a current I to the external resistance R. Okay, now this I, when it is going through here, it will remain I up till this point. But at this point, this current will have two options or two paths. So the current will definitely be divided. We all know that in parallel current is divided. So let's call this current as I1 and this current as I2. Okay, if I'm talking about the naming of the point, I have called this point A. So I'm calling that this point is A, to which the external resistance is connected, and this point is B, to which the external resistance is connected. Single cell, when replaced by, so when a single cell replaces these two cells, so I'll assume that between these 2 points A and B, instead of two cells, a single cell is being used. So this cell is doing the same work, that is, it is also flowing the same current I through the external resistance R, and that current was being flown by these two cells. So now I have to find the value of E dash and R dash. How I'll do it? It is the point of our topic. Okay, so let's focus on this topic. Okay, now first of all, look at this cell. This cell is also connected between point A and B. This cell is also connected between point A and B. Now both these cells, E1 and E2, they are connected between points A and B, so they both will have the same potential. I'll say E1 and E2 both are connected, both are between points A and B. Okay, so their potential difference will be equal. So their potential difference will be equal. Let's call their potential difference as V, and by V I mean VA minus VB. I am taking the liberty of taking A as a point of higher voltage because A is connected to the positive terminal of the battery. So now this is the first equation that I am taking. Okay, now for the first cell, that is, its EMF is E1, its internal resistance is R1, the current that is flowing through this branch is I1. This point is A, this point is B. So now if I apply the formula of voltage, this formula, okay, voltage across 2 points is equal to EMF minus current into R, and R is the internal resistance of the cell. So when I apply this formula for this cell, then what I will get? I will get VAB, and I am calling VAB as V equals to E1 minus I1 into R1. Okay, because the internal resistance of this cell is R1, the current that is being flowing, that is flowing is I1. So the potential difference across this cell is V, its EMF is E1, current is I1, its internal resistance is R1. So also for second cell, its EMF is E2, its internal resistance is R2, the current that is being flown, or the current that is flowing, is I2. So what I can write about the potential difference of this cell? The same equation I can write VAB, that is V, it will be equal to E2 minus I2 R2. This will be equation number 3rd. Okay, and when I am talking about this single cell, because this equation is not of that much use. Similarly, for this second cell, okay, I have to find the value of I2. So what will be its value? I'll write like this: I2 into R2 equals to E2 minus V. So I'll get I2 as E2 minus V upon R2. Now let me call this equation as 3rd because I don't need this equation. Now one thing is for sure, and that thing is, since the current I is divided into I1 and I2, so I can always write that I1 plus I2 will be equal to I, because I is the current that is being divided here. Let's call this equation as equation number 5th. So I have got the value of I1 by equation number 2nd. I have got the value of I2 by equation number 3rd, and now I will use the values of I1 and I2 and I will put them in the equation number 5th, so that I can bring equation something like this. Okay, so now which all equations I am using now? I am using equation number second, third and fifth. Okay, that is this equation, and this equation. So let me write it once again. Okay, I1 plus I1 plus I2 equals to I. So I'll put the value of I1 and I2 here. So when I'll put the value of I1 and I2 here, what I will get? E1 minus V upon R1, E2 minus V upon R2 equals to I. Okay, now I will rearrange it and look at this equation. This equation also contains a term of I. I will rearrange this term, this equation, and I will isolate I by this equation directly now. By equation fourth, let me isolate this term I. How I will do it? I will do it by this. I into R dash equals to E dash minus V. So I will be equal to E dash upon R dash minus V upon R dash. Now let me call this equation as equation A. Okay, so this is the value of I that I am getting if a single cell is used, and if I am using multiple cells, then also I am getting the value of I. So now I will bring this equation in a form comparable to this form. So the term that will be divided by V will be the equivalent resistance, and the term, okay, will dividing the term that will divide E dash will be equivalent resistance. I can take LCM also, whatever I can say, but first let's simplify this equation. So how I will simplify it? Take LCM. So E1 minus V into R2 plus E2 minus V into R1 upon R1 R2 equals to I. Now also I am not able to compare these two equations because this is something like this. I want to isolate V and EMF. So let's isolate V first. So I will isolate V first. So how I will isolate? E1 R2 I will write here, E2 R1 I will write it here. Now I have to isolate V first. So what is the term of V here? Minus V R2. What is the term of V here? Minus V R1. Okay, R1 R2 is dividing both these terms. I can take minus sign as common and V as common, but let's do one thing at a time. Okay, now the equation becomes like this, and this value is equal to I. Okay, now we can compare, but let's simplify it a little better. Okay, here you can see that V is alone in the numerator, but here V is not alone in the numerator. This term is also in the numerator. So let's bring this, and this term will become minus V upon R1 R2 upon R1 plus R2 equals to I. And about this term will be E1 R2 plus E2 R1 upon R1 R2. Now I will compare this equation by this equation. The first thing that you will notice is that here V is single, here also V is single. So here V is being divided by the equivalent resistance. So whatever is dividing V is equal to equivalent resistance. So we can say that the equivalent resistance R dash will be equal to R1 R2 upon R1 plus R2. This is the formula that we get in parallel. Okay, so if two cells are connected in parallel, then their equivalent resistance can directly be obtained by using the formula of resistances in parallel, because resistances will not make any kind of difference because they don't have any polarities like plus and minus. So now we have got the value of equivalent resistance. What I have to find now? I have to find the value of equivalent EMF. Here you can see that the denominator is equivalent resistance, but here it is not equivalent resistance. Otherwise you can say that here it is I, here it is I, here it is positive term is net EMF बटे में net resistance, here it is this term. So we can compare and I can say that this term E dash upon R dash is equal to this term. Okay, so it will make our task a little bit easier. So I will say E dash upon R dash will be equal to E1 R2 plus E2 R1 upon R1 R2. But this is not easy to remember. So in order to simplify it, we can do a little bit of editing here. So what type of editing I will do? Otherwise I can directly remember it, but it will not be that easy to remember. So what I will do, I will divide and multiply the denominator by R1 plus R2. Then the formula will become a little bit easier to remember. I can do it like this, or if I don't want to do it like this, then let's forget this. Okay, just remember this equation is equal to this equation. Let's move on. We were at this step that net EMF upon net resistance is equal to E1 R2 plus E2 R1 upon R1 R2. Now let's separate the terms. So E1 R2 upon R1 R2 plus E2 R1 upon R1 R2. R1 will cancel out from here and R2 will cancel out from here. Now the formula will be easier to remember. So this is the formula that we get when two cells are in parallel. To find the equivalent resistance, you can directly use the formula of resistances in parallel. And to get the net resistance in parallel, you have to use the formula like this. That net EMF upon net resistance is equal to EMF of first cell upon resistance of first cell plus EMF of second cell upon resistance of second cell. Let's solve an example and then you will get a little bit of more understanding of this. Let's say we have two cells. It is of 10 volt EMF, its internal resistance is 2 volt. It is of 20 volt, its internal resistance is 1 ohm. Okay, I want to replace, so I will use 1 upon R dash will be equal to 1 upon 2 plus 1 upon 1, because this is the formula for resistance in parallel. Take LCM 2, here it will become 3 by 2. Now don't forget to reciprocate it. Most of the students forget to reciprocate it. So the first task is done, that is, if we replace these two cells by a single cell, then its internal resistance will be 2 by 3 ohm. Let me write it clearly, 2 by 3 ohm. Now the second task is to find the EMF. To find the EMF, I'll have to use the formula like this. Net EMF upon net resistance equals to E1 by R1 plus E2 by R2. So here E1 is 10, R1 is 2, E2 is 20, R2 is 1. I will write the formula like this. Net EMF upon net resistance. Now I know net resistance is 2 by 3. So let's write 2 by 3 here. Now E1 by R1. E1 is 10, R1 is 2. So 10 by 2 plus E2 by R2. E2 is 20, R2 is 1. So what it will become? It will become 5 plus 20. It is 25. So 25 is not the answer. 25 is equal to 3 E dash by 2. So E dash will be equal to 2 into 25 upon 3, that is 50 by 3 volts. So if I want to replace these two cells by a single cell, then the EMF of this single cell will be equal to 50 upon 3 volts, and its resistance will be 2 by 3 ohm. Now let's solve one last example, and in this example I will take more than two cells so that you can get a better idea of this. Either you will get a better idea or you will be scared of this, but you don't need to prove it. You just need to remember the formula. If instead of two cells there are multiple cells, then how we will use the formula? First we'll find the internal resistance of the cells. To find the internal resistance of the cells in parallel, we all know that the formula goes like this. If there are n cells, the formula will go like this for finding the net internal resistance, and for finding the net EMF, then net EMF upon net resistance will be equal to E1 upon R1 plus E2 upon R2 and so on. I can also use the En upon Rn. I can also use the formula of summation. Okay, I can say that 1 upon net resistance is equal to summation of I from 1 to n 1 upon Ri. And for this I can also use the summation term. I can say net EMF upon net resistance is equal to summation of I from 1 to n and Ei upon Ri. But if you are not familiar with this summation term, then you don't need to worry. Just do it any number. Obviously n can never be negative because you cannot use negative number of cells. So let's solve an example considering 3 cells.